Hi everyone, and welcome to this episode. Today we have Marta Estarellas with us, who's representing Qilimanjaro. Qilimanjaro is a company that's building quantum annealers, and for those of you who are unfamiliar with that kind of technology, it's a specific form of quantum computers used for optimization tasks. We're going to be talking about the general industry as a whole, where it's headed and its overall direction and obstacles. But we're also going to talk about the enhancements that Qilimanjaro is working on specifically, and the issues that Marta is dealing with on a day-to-day basis. I hope you enjoyed the discussion, and let's dive into it. Hey Marta, thanks a lot for joining today.
Thank you, Niklas.
I figured we could kick off the discussion by just talking briefly about Qilimanjaro and the offering you have. Just on a very high level, we'll get into the details of the different infrastructures and topics that you're working on, but if you want to just introduce the company very briefly and the key offering that you have.
Yeah, absolutely. So Qilimanjaro is a full stack quantum computing company. It's based in Barcelona. It was founded in 2019, but it was not until 2020 that we really started operations. We started building the team and started having clients. We focus specifically on analog quantum computation, even though we are also delivering digital systems. But our true innovation relies on what we call quantum app-specific devices that we also call QASIC. And this is part of our philosophy. So we want to push the chances of bringing quantum advantage now as soon as possible by making this offering of trying to bring as close as possible the design and the development of the chip, which we based on superconducting qubits, to the design of the algorithm to tackle the use case of an interesting use case of the industry that can be optimization problems in the industries of logistics, finance, energy, but also quantum problems in academia, in physics, in chemistry, material science, and so on. So this is what this is our philosophy in terms of innovation. But in parallel, we are also offering some services to clients already. We work as integrators in terms that we can pack together a quantum computer from different technologies and all the quantum enabling components that it needs in terms of control, in terms of measurement, in terms of refrigerators, cryogenic units. And we can deliver this. We can put everything together, we can mount it, and we can deliver to the client's premises. This is an offer that we've done in the past in Abu Dhabi at TII. And this is something that we are currently doing at BSC, the Barcelona Supercomputing Center, which is one of the biggest HPC centers in Europe.
So the people that approach you for those specific requests, are they looking to set up a front-to-back quantum computing system, and they are looking for advice in terms of what products to get? Is the main problem that they're trying to circumvent that they don't know what kind of components they want to actually purchase from the market, and that you have the expertise already to deliver that? Because I suppose you're not fabricating any of these components yourself.
Well, we do have two routes, right? One is the innovation, which I was mentioning about these QASIC systems that are analog and they are based on flux qubits. So this is our own value proposition in terms of architecture and in terms of chips. And we do fabrication, so we do have a team of fabrication experts of flux qubits. But on the other route, we do have the one more commercial proposal, which relies on third parties components. So we use chips from other companies, other vendors, and also components in terms of control electronics and so on. And the typology of client that wants this service is usually a research institution or an HPC center that they want to start learning and experiment with this type of devices. But the expertise that is required to pull everything together is very niche, is very difficult to find. And it requires not only hardware experts that have done this before at least once, it also requires software experts that are capable of mounting all the software stack, because at the end of the day, those users will have to interact with the quantum computer in a remotely manner. So we need to build a software stack that allows you to have some sort of cloud service and access to the system, and also some sort of operation and operation system framework with some language that the user can really understand to interact with the quantum computer. And on top of that, they also often need some guidance and some consultancy on how to translate their use cases, their problems into a quantum algorithm, because this is also an expertise that is still not widespread in all the industries. So they often require from us this guidance on understanding very well the use case, also identifying if it makes sense to make it a quantum algorithm or not. Not all the use cases, not all the problems can have an efficient quantum solution. And then we help them to develop the algorithm that would tackle this problem.
Mm-hmm. I want to go into the details of the architectures that you're developing, but since we started on the trajectory of software-oriented development, maybe we can stick to that path for a little while as well. So you build, I assume, specific algorithms in some cases for clients, or help them to develop their algorithms perhaps, and you also build a full software stack for your quantum computers that you're developing yourself, and you have an open source repository which probably has some overlap to this, called QIBO Lab. Is that the proper name of the...
QIBO.
Just QIBO, okay.
Mm-hmm.
Okay, so could you perhaps put QIBO into context when it comes to the software that you're already developing for your solutions, and what the intention is behind that open source platform? Absolutely.
So QIBO is an open source programming framework for quantum computers. These efforts were initiated by some of our co-founders, the co-founders of Qilimanjaro, but now it's much more widespread, so it has a lot of contributors, mainly from the TII, the Technological Innovation Institute in Abu Dhabi, but also at CQT, at the Center for Quantum Technologies in Singapore, and also CERN. So we do have important contributors from CERN to this effort. And this is if we look at the stack top to bottom, QIBO would be on the top side. So this is what allows you to program your circuit, your Hamiltonian, your algorithm in terms of all these elements that you can pull together. So a sequence of gates or different schedules for interpolating in your annealing path if you are doing some adiabatic algorithms. And this is the top layer, if you like, the application layer that the user will use to program their algorithms, but then when we have to go deeper, right? So once you have the circuit, once you have the algorithm, in terms of sequence of gates or in terms of annealing schedule, you have to translate everything into language that the quantum computer will understand, which at the end of the day with superconducting qubits, it's a sequence of microwave pulses that you send to your qubits. And this is done with more inner layer that is called QIBO Lab. QIBO Lab is doing this, and this is open source in this QIBO framework, but we also internally have a non-open source framework that is called QILab. And this QILab only focuses on our systems. QIBO Lab focuses on a wider range, because the nice idea of this QIBO framework is that it's hardware agnostic, in the sense that it can not only connect to superconducting qubit backends, but it can also connect to classical simulators, which is very useful when you want to run benchmarks, but also different quantum backends. You could think of ion traps. I think in CQT they are actually connecting QIBO with ion trap devices. So that's very nice, because a lot of the other software stacks are focusing only on one technology, but this one is a more open way of encoding your problem into quantum computers and simulators. And that also allows you to run a lot of benchmarks, because if you would have available all these backends at the same time and you have the same problem encoded in the same language, then you can just execute it in different backends and compare how the results differ. So that's the idea behind this open source programming framework.
Okay. One question that I have when it comes to this framework is how generalizable it is in terms of the architectures that you can apply it to. So you mentioned that in theory, at least, you can apply it to multiple different backends. I had an interview with another researcher recently who was talking about different ways that you can characterize quantum computers in a better way. The issue being that when you actually want to calibrate your quantum computer, there's a lot of intricacies surrounding that particular computer. So if you want to have a good model of your quantum computer to provide accurate measurements, for example, the process currently of calibrating these is quite lengthy. That's my understanding. When it comes to applying a framework like this to a wide set of quantum computers, how do you facilitate that kind of calibration approach, if at all? And is that necessary if you want to build, let's say, an algorithm for multiple different hardware platforms and you want it to be compatible and also accurate with those? Do you need to couple a system like you're developing now with something more hardware specific that does sort of a calibration of the model for you and then integrates with this solution?
Yeah, so calibration is a very important topic. This is something that needs to happen very often because otherwise you cannot use the computer anymore. And that's very, very much dependent on your hardware. And as you said, every specific hardware will have a different set of control electronics associated to it that will allow this calibration. And each of these control electronics will have different drivers to interact with your software stack. So what we do is to try to include to make sure that the lower layers of our software stack can speak with as many of those control electronics as possible, so we can do the calibration with a wider range of systems. But this is a challenge in this stack because we don't have a standardized instrumentation. Each instrumentation, I mean, just for superconducting qubits, you have different control electronics from different commercial providers. You have Q blocks, you have Zurich instruments, you have quantum machines, and I'm sure I'm missing many more. But all of them work in a different fashion. All of them have different languages, and all of them need different drivers to interact with the higher layers of the stack. So you need to make sure that your low-level stack can speak with all these electronic components in order to make sure that you can speak with a wider range of architectures. And that's a challenge. But it's just a matter of including more and more drivers to your stack.
Mm-hmm. If we compare digital quantum computers to analog ones, you noted in the beginning that you're primarily focused on analog ones, but you also have some involvements when it comes to digital quantum computers. Does QIBO apply to both of those? And are there a lot of different design choices, you have to make to facilitate integration with those two kinds of architectures?
What do you mean by integrate in the hardware level or in the software level?
Both, I would say. So writing software compatible with analog and digital, is that a fundamentally separate process? And also on the hardware layer, when you want to connect, I assume there are some differences.
Okay, so what I was saying is that is a very interesting question. Usually we separate completely what is analog from what is digital. With QIBO at the software level, we can design algorithms for both, but in a separate manner. So the user needs to make the choice whether the algorithm needs to run in a digital computer, and if so, the user is going to create a sequence of gates with some constraints, or whether the user wants to run the algorithm in an analog device, in which case the problem is going to be encoded into a Hamiltonian and with some time constraints on how the system needs to evolve. At the low level, at the hardware, these architectures are completely different. So in general, at least in our case, for the digital computations, we use chips with transmon qubits, which is one type of superconducting qubit. It's the canonical superconducting qubit that is used for many other groups and many other companies. And for the analog part, the architecture that we use is flux qubits. So completely different chips, completely disconnected. Now, one very interesting question is is there a chance to integrate both? Is there a chance to have a hybrid proposal, a hybrid hardware solution, and also hybrid software solutions? And this is something we are very much exploring. This has not been done at the hardware level, but there are many ideas on digital analog hybrid quantum algorithms, which mix a little bit the analog processing with the digital processing. This is something that was mainly initiated by Professor Enrique Solano. When he used to be in the Basque country. And it's this idea of having circuits where the single qubit gates are done digitally, but the 2 qubit gates, which are the ones that are promoting entanglement, are done in an analog fashion. So you let the system evolve through the Hamiltonian, so the natural dynamics of the Hamiltonian of your chip, and this gives you some entanglement if you do things precisely. The problem with this model at the practical level is how you do the switching on and off of the digital analog part in your circuit, which induces some errors. But this is something we are exploring because we think it's a very interesting solution to mix different architectures, and yeah, research-wise, this is very exciting to look at.
Is there a reason why the split between, or the way you merge the two architectures is the way it is? Like that you use the digital version for single qubit operations, and then when you need entangling, the analog one would kick in, so to speak. Is there a reason why the proposal is to make it that way as opposed to the other way around? Do analog quantum computers generally perform better when it comes to entanglement tasks, or is there some other reason?
I'm not sure about this one. I will need to check the paper again, but I think it was a matter of efficiency in generating the entanglement. So it's more efficient if you do it through the natural dynamics of the system than if you apply the gates. And I think there was also some pro of doing it this way in terms of the errors that you introduce from the 2 qubit gates. So instead of having a long sequence of 2 qubit gates that generally introduce you some errors into your circuit, you would have just a natural evolution that would mediate all these entanglement interactions, and that would save you some circuit depth, and it would also save you some errors that get introduced into the computation.
Mm-hmm. When we talk about circuit depth in that context, are we looking to limit circuit depth because it's inherently a lossy process that you want to have as simplistic circuits as possible to just prevent errors from being introduced in the computation? Yeah,
absolutely. So if you think of circuit depth at the end of the day is the length of your circuit, which comes determined by the number of gates that you have in the circuit in a sequential manner, and each single gate that you apply introduces an error. It's a small error, but you get it there, and the problem is that those errors accumulate. And the longer the circuit is, the more errors you accumulate at the end of the circuit. And once you measure it is often the case that the error is so high that you cannot make sense from your qubit state anymore. So the shorter the circuit, the less errors you have, and on top of that, we are also constrained by the coherence times of the qubits, which is basically the lifetime of the quantum information in the qubit. And the shorter the circuit is, the more comparable, the more within is these coherence times of your qubits, and you can guarantee less errors also from the environment, not also from the introduction, not also from the control that you apply to the system. So we will eventually, and I'm very confident about that, we'll have error correction protocols based probably on the surface code that would allow us to mitigate these errors from occurring. But until now, we are in this NISQ, noise intermediate scale quantum computing era. That means that we are very much limited by the noise, by the coherence times of our qubits, and by the errors that we introduce to them. So we want to make things as short as possible to mitigate those.
I want to stick on the concept of coherence time actually, but I think we should introduce quantum annealers first and some of the background associated with that, and then we'll return to that concept. So if you want to just describe what a quantum annealer is, given the fact that you're putting a large emphasis on this particular topic, just to set a small bit of background for the listeners.
Absolutely. So quantum annealers are a way of doing analog quantum computation. So analog quantum computation is much more than quantum annealing, but quantum annealing is one very popular set of algorithms to do quantum computation. The key of quantum annealing is that you encode your problem. Generally, typically is an optimization problem, but it can be more than that. But the key is that you encode this problem in such a way that you put it into a Hamiltonian, into the form of a Hamiltonian. And if you do this encoding right, you can guarantee that the solution of your problem is going to be codified in the ground state, in the state of minimum energy of this Hamiltonian. This mapping is usually done through with problems that can be formulated into a QIBO problem. This is what is usually called a QIBO problem. At the end of the day, maps a minimization function with some constraints. And this minimization function with some constraints can be directly mapped to a Ising Hamiltonian. Hamiltonian with ZZ interactions and Z local fields. If this mapping is done correctly, then again, your ground state encodes the solution. Now, the problem of this is to reach the ground state. So it's not trivial. It's not just a matter of encoding the problem and, hey, I measured the ground state. That's not easy. So the key component in terms of control of quantum annealers is how to reach this ground state. So what is typically done is that we start in the ground state of a different Hamiltonian that is very easy to prepare. So usually it's the Hamiltonian that has a longitudinal field, only sigma x in each qubit, which ground state is the superposition of all the basis states of the system. So superposition of all the possible options. And this is relatively easy to prepare. And we guarantee that we are in the ground state. And now the key component to how to go from one to the other is that is what's called the adiabatic theorem. The adiabatic theorem what says that if we interpolate slowly enough between the initial Hamiltonian and the final Hamiltonian that encodes our solution, assuming that we start in the ground state, we can guarantee that we will always remain in the ground state. So you do the interpolation slowly by changing the Hamiltonian parameters such that it brings us from the initial Hamiltonian to the final Hamiltonian. And by doing this, we can guarantee that we will always remain in the ground state of all the intermediate Hamiltonians that drive this interpolation. After this process has happened, then it's just a matter of measuring the ground state, your final state, which, if you've done it correctly, should be the ground state of your final Hamiltonian.
Mm-hmm. One question that I have on this, so this is a bit interesting to me. I feel like it's a bit unintuitive maybe that theorem exists. Like if you have a driving Hamiltonian, so your starting point, and then your target Hamiltonian, and you want to go in between these two, the theorem is essentially saying that if you prepare it in the right way, you can traverse this trajectory slowly and get to the other side without ending up in another state. Mm-hmm. Is there some conceptual way of thinking why there are no overlaps in terms of other states that the system could end up in? I know in previous presentations you had good illustrations of this, where you have a graphical representation of the trajectory you would traverse, and the ground state that you're looking to follow is always at the bottom of this trajectory. Do you have some form of guarantees that other states that the system could end up in will not be sufficiently close so that really becomes a problem? How maybe that question is quite loose, but I'm thinking, why is it the case that you can traverse this sufficiently slowly and not end up, for that reason, in another state that you're looking for?
Yeah, so put it in a very conceptual manner. If you have a quantum system and you ensure that your initial state is one of the eigenstates of the quantum system, that will remain static, so it won't evolve. If instead you have a superposition of eigenstates, that will have some evolution through the Schrödinger equation. But if your initial state is one sole eigenstate of the system, that remains static, so that doesn't move, that doesn't evolve. Maybe it might acquire a global phase, but that won't move. Now, how can we profit this and at the same time change the Hamiltonian? So you change it with a very small delta, such that the next in this interpolation you go to the next Hamiltonian that has a very, very tiny difference. And if you do this small delta slowly enough, so if you ensure that this delta is very, very small, you can also approximate the system to be in that ground state, and that means it's going to be static. So that means it won't move it won't evolve. It will acquire a global phase, but it won't jump to other excited states. And if you keep doing these very, very slow deltas, the very slow interpolations, you will guarantee that you are always in the ground state, in the eigenstate of your system. You could do this in a different eigenstate, so it doesn't have to be the ground state. You can do this in a different eigenstate. But the key aspect here is that we do in the ground state. Now, if you do things a little bit faster, you are introducing some energy into your system, and this risks your system to jump into an excited state, depending on the gap. So, if the energy that you introduce is comparable to the gap between the ground state and the first excited state or some other state, your system will jump to that other state, and here you will start having some evolution that goes beyond this static concept of remaining in the ground state. This might be useful, by the way, so this is not necessarily a bad thing as long as you do it in a controlled manner. So usually we understand annealing as an adiabatic algorithm, that we want to remain all the time in the ground state and do things slowly enough and ensuring that the energy that you introduce is not such that you jump. But you can also think of finding what we call shortcuts to adiabaticity, which is in a controllable manner jump to an excited state and then go back down. And there are some techniques to do this, but for that is really, really important, and that might bring to the next important point of this technology. It's really important to have coherence in order to have a controlled manipulation of the state and the dynamics of your system. You need to ensure that your system is coherent.
When you talk about shortcuts in this context, so moving from the ground state to an excited state to then return to the ground state again, would that be a technique to reduce the amount of time required to traverse the trajectory, or is there some other benefit to it as well?
It's about time. So the annealing time comes limited by what is called the minimum gap. So if you think about this interpolation between the initial Hamiltonian and the final Hamiltonian, each intermediate Hamiltonian will have a different spectrum, and the energy between the ground state and the first excited state, which is the next one, will change. So this gap between these two energy states, will change during the interpolation. And the most delicate part of this interpolation is when this gap is minimum, because it's when it requires less energy to jump. So when you pass through this minimum gap, you need to do it specifically slowly, so you ensure that the energy that you introduce doesn't give you that jump. Sorry, I lost a little bit the question now.
I think so. We were talking about whether you could, what you mean by shortcut, that you could excite the state and then maybe end up taking a shorter path through this adiabatic trajectory. Yeah.
Exactly. So in this minimum gap that is limiting the speed of your overall algorithm, you could think of circumventing it by jumping to the first excited state. You don't care. So you don't care about jumping anymore, so you can actually go through this minimum gap in a faster way, jump and then go back. So that would be the idea of getting around the slow requirements of going through the ground state in this minimum gap region, jumping and going back.
Okay, and that would be a very specific solution for the kind of situation where you have a very small gap locally, let's say. The reason why I'm asking that is my understanding is the delta between the different energy states generally becomes smaller the more excited your state is, right? So in general, I would assume that the most stable state is actually the ground state, but that you then, for local sort of problems with the adiabatic trajectory, could then shortcut. Is that also your understanding?
Yes, and there's also an important factor that the bigger the system is, the smaller the minimum gap is. So the minimum gap scales badly with the size of the system. So one thing is to have an annealing path, an annealing algorithm with 5 qubits, and the other one is to have an annealing algorithm with 5,000 qubits. So that makes the gap much smaller. And if we think of how we are going to scale this technology, it's very obvious that we will need to find ways of circumventing this scale down of the minimum gap. And using these adiabatic trajectories is a shortcut, is a way to avoid the situation of the scaling of the gap.
Okay, understood. How many parameters do you have when you think about optimizing this kind of system? From a design perspective, so obviously we have the coherence time, you could make that longer and therefore you would have more time to traverse this trajectory slowly. You could also have ways, as opposed to extend the gap between the different energy states. Are there any other, let's say, primary parameters that you could modify here to make the system more stable?
Yeah, so for instance, in the annealing algorithm, there are no unique ways to interpolate between the Hamiltonians. If you think about it, you could think of a linear interpolation between initial Hamiltonian and final Hamiltonian, but you could also think of a quadratic interpolation. So that's an important degree of freedom that the user has in order to find, to optimize the algorithm. There might be an interpolation between the Hamiltonians that give you a wider gap, and that it might be advantageous in terms of efficiency and time. Other parameters that you can tune is, of course, the Hamiltonian parameters. You can think of different Hamiltonians and different ways to encode your problem. The Hamiltonian parameters typically are the qubit energies. This is something that you can generally tune, and also the way the qubits interact. And the way the qubits interact, they interact with an energy as well, so you can also tune these energies. Typically in the analog systems you have freedom to tune these two parameters, and actually it is by tuning these parameters that you can interpolate from one Hamiltonian to the other, otherwise you couldn't. So it's by changing these elements that you can go from one to the other. And at the hardware level, this translates into pulses that you send, or flux biases that you modulate from different components of your circuitry. And you have some flux bias that you can modulate at your qubit level, and this allows you to change the energies of the qubit. But also you have some flux bias that you can modulate at the couplers between the qubits, and that effectively changes the energies that are associated to the interaction between these two qubits. Another important aspect, and this is something that we do quite differently in Qilimanjaro, is the ability of having different types of interactions between the qubits. So you can have, let's say that let's put it simply, you have 3 dimensions. You can make the qubits interact in 3 dimensions: the XX, the YY, and the ZZ interaction. And these 3 ways of interacting the qubits give different properties in terms of how the system will evolve. But also it gives you the freedom and the versatility to encode a much richer variety of problems into your Hamiltonian. If you only have the way to make the qubits interact through a ZZ interaction, which is, for instance, what usual annealing hardware is allowing you for. It's only to have Z-Z interaction, to only do icing problems. Then you cannot encode, let's say, a purely quantum problem, such as a chemical, a molecular structure into the Hamiltonian, because the electronic structure of molecules, its Hamiltonian will need an XX or an YY interaction. So what we are working in Qilimanjaro is in different architectural designs that focus very much on guaranteeing that the coupling between the qubits can also allow to go beyond the Z-Z interaction. And this is challenging in the sense that you not only need to guarantee this interaction, but you also need to guarantee that you can independently tune them to do what I was saying before, to have the control to change the energies between each different coupling interaction.
What is actually the effect of changing this coupling energy? So can we say something conceptually about what a high coupling energy would entail and what a low one, how a low one would perform differently? Like, what's conceptually the difference in terms of functionality for the system when we change this energy?
So one thing is a strong coupling and the other one is the weak coupling. So the stronger the coupler you have, so it depends on what you want to encode, right? In dynamics, the stronger your coupling is, the faster the dynamics will go through this interaction, and the weaker, the slower it will happen. But the having the versatility to have strong or weak or different regimes of interactions is very much related to the problem that you have, so to the encoding that you have to do. And it's just a matter of having the flexibility to be able to tune in different energy regimes. So for instance, a molecule or an optimization problem that is encoded into a Hamiltonian might have, due to some constraints, the requirement of having in certain parts of the topology graph of your qubit, of your hardware, stronger couplers than another part, just due to the nature of the problem. And that's why it's so important to have the versatility of being able to encode that, because at the end this is the let's say the constraints that you have on the hardware that will determine how the eigenspace, how your eigenstates are constructed, in a sense. And in annealing, as we say, the ground state and the basically the eigenstates of your Hamiltonian are what determine the solution space of your problem. So you need to make sure that you have this one-to-one mapping.
Mm-hmm. In determining the target Hamiltonian for a system like this, is there a recipe, so to speak, for the kind of steps you would take to actually arrive at that? So conceptually it's clear, you construct or you prepare the system in the right way, the answer to your optimization problem is encoded in the Hamiltonian, but how do you go from an optimization problem to a Hamiltonian that you want to construct?
Yeah, so is this QIBO process. So a wide variety of optimization problems can be written in a mathematical way, in a binary way, such that each binary string encodes a solution. And what you want to do is to minimize a certain cost function that has the constraints of the problem. So it's the solution, the binary string that minimizes this cost function is your global optimum, is the one with minimum energy. This is the way optimization problems are usually mapped formally. Now, these cost functions, these minimization functions that are minimizing a set of binary strings, can be mapped into an icing Hamiltonian. So there's a one-to-one, very straightforward mapping from the elements of this cost function into the elements of an icing Hamiltonian. So when you have constraints that imply interaction between the binary strings. This translates into a ZZ interaction between qubits. And when you have energy constraints that only affect one of the binary elements, that translates into an energy gap into your qubit, your single qubit. So you can map pretty straightforwardly this formalization in binary language into the formalization into a Hamiltonian language.
Mm.
The challenge comes in the interconnections. So optimization problems are usually regarded as graphs, where each node is either a possible solution or is just a part of the problem or a constraint. And mapping this into a quantum computer is challenging because it is often the case that those graphs are very densely connected. And if you think of how quantum computers, the hardware typically works, they tend to be planar chips, right? So if you want to have very dense connectivities between the qubits, that becomes a very, very big challenge, because that means that you need to put a lot of couplers in between. So if you want each qubit to be connected to every qubit, that's impossible, in the sense that you will need so many circuit elements that will cross one to the other, that you would have what is called a lot of crosstalk. Crosstalk is when some elements of your circuit or your hardware start interacting with the others and causing errors. So that's a bit challenging, and And the ways that there are out there to circumvent this situation is to have some what is called graph embedding techniques that allow you to use some ancillary qubits to mediate the interactions that you don't really have in the hardware, because the degrees of connectivity that you can put in the chip, in a superconducting chip at least, are very, very low. Let's say a degree connectivity of 6. So let's say that each qubit can speak with, or can see, or can interact with 6 other qubits, but that's it. So if you have a chip of, for instance, D-Wave has a chip of 5,000 qubits, if you want each qubit to speak with 5,000 qubits, that's not doable. So what they have is these sparse graphs, and what they do to encode the problem is to have a pre-processing that runs in a classical computer to find the right mapping of the graph that you would ideally want to the topology that you actually have, by using these ancilla qubits to mediate the parts that you don't have. It's challenging.
Right. If we think about how we would take the current state of annealing quantum computers and turn them into general adiabatic quantum computers, like in the most general form, is the main problem that we're facing currently these kinds of hardware encoding problems, or is it more related to the translation between, let's say, the Hamiltonian and how you would actually encode that in a system? Because those are the two problems I see, but I don't know if there are even more problems here. Probably there are, that I'm neglecting at this point.
Yeah, so adiabatic quantum computing has the potential to be universal, in the sense that it is equivalent mathematically to digital quantum computers. Why is it often, though, regarded as a model only for optimization problems? Because of the difficulties of having different Hamiltonians as the final Hamiltonian. This goes very much aligned with what I was saying before about going beyond the ZZ interaction. So if you allow to have different types of interactions in your hardware, of course that means to have different components, different architectures in your hardware and in your circuit. You have a wider range of problems that you can encode into the Hamiltonian. So if, let's say, you would have the chances to do XX, YY, ZZ interactions, then you would have a universal platform. You can encode any arbitrary problem without having to rely in a very big qubit overhead or any approximation. So that would be one of the main challenges and one thing that we are actively pursuing. The other challenge for universal quantum computation with adiabatic systems is the same challenge that we have with digital. Eventually are the errors that we have. So we need to make sure that the qubits, the different qubit architectures keep increasing in terms of coherence times. Even though the qubit architecture that is typically used in analog systems, the flux qubits have much longer coherence times than transmons. So that's actually why this type of qubits are preferred for analog devices. That's one of the reasons. But we need to still push the coherence times much higher. And also to be able to control what we were talking about, these diabatic transitions. Because if you don't have this coherence, you cannot control that in a precise manner. And that also goes in line with the scaling of the technology. So the more qubits you have, the more challenges you have in terms of errors. Crosstalk is a big issue, as I said before. So mitigating crosstalk is something that you can do at the software level. You can compensate the errors that you have by doing some calibration. So by calibration, you can compensate for crosstalk, even though it gets more and more challenging as your system gets bigger. But you can also avoid crosstalk by finding different designs in terms of the hardware at the fabrication level. One ways that we are also exploring is to go beyond the planar chip and think about 3D chips, so 3D packing of the architecture. But those are very novel strategies for design and fabrication. But then they need to be pursued, because otherwise when we want to go to very big systems, that's going to be a big problem that we are going to encounter. So those are the main challenges to overcome these problems. Error mitigation, it will also be eventually an issue. So adiabatic quantum computing has this advantage in the short mid-term that is not so vulnerable to errors, because you are doing this ground state computation, but you still have errors. So when you do the interpolation, when you do the control that is required to do the annealing path, the annealing schedule, you are introducing errors to your system. So the bigger the system is, the more errors you will have. And learning how to mitigate these errors, or even thinking about error correction protocols for adiabatic quantum computation, which is something that has not been very much thought, that would also be eventually necessary.
Okay. I see that we're starting to roll up on time. I would just want to check from your perspective also at this point, looking forward, let's say a year into the future, what the key targets are for Qilimanjaro in terms of things you want to enhance, be it on the hardware side or the software side.
Yeah, so our goal for 2023 is to finish. So we are working on our prototype that shows all these architectural elements that we were talking about, and is to release it and to show it to the public. We're very much working on different iterations on this prototype. Then early 2024, we want to put some of our prototypes to the cloud. So we want to open our quantum as a service. So this is something that we have almost ready to open to the public, and we really want the users to start playing with our technology and get some feedback from these first users. We are also working on the sequence of deliveries to this Quantum Spain project, which is a big Spanish initiative to bring the first quantum computer to Spain, and we have a sequence of deliveries that increase in complexity of the chip that they acquire, and we want to fulfill very much these deliveries and ensure that those are very good performing quantum computers. And with these deliveries, we also provide our quantum as a service. So that for us is also going to be very, very interesting to see to get the feedback from typical HPC users on our software stack. And Of course, we keep engaging with clients from different industries, and that's a very important exercise for us because we come from academia, right? And we need to very much understand what is the market need for quantum computation in order to guide in the right path or product strategy and our value proposition. So we mentioned earlier that one of the key philosophies that we're pursuing and the key product that we are developing are these quantum ASIC. Those are app-specific devices that are targeting a specific use case. And for us, it's very important to understand what are the interesting use cases for the industry. And those exercises that we do in terms of working in identifying use cases with a client in the energy sector, in the finance sector, in the logistics sector, are very important for us because it allows us to drive the internal developments that we have in terms of these QASIC chips. So that's a little bit the prospects of Qilimanjaro for this year and next year, to keep continuing on delivering our promises to our clients, and also incorporating all this knowledge on the market to drive our innovation products.
Mm-hmm. The last question I would have is for any other companies out there that are listening and that are investigating whether they would want to break into the space in terms of utilizing quantum as a service. Is there a particular aspect of your offering that suits a particular client better? And who would you say should come to you as opposed to coming to some of the competitors? What is the offering that sets Qilimanjaro aside in that aspect from other players?
So in terms of applications that we can cover, we very much align with optimization problems as an annealing, as our analog systems can encode annealing problems. So all the industries that have optimization problems, such as industries of, I'm thinking of logistics, deliveries, optimization of deliveries, optimization of warehouses, also in the energy sector, they do have a lot of the optimization problems in terms of market pricing, in terms of optimizing placing of different units in their systems. All these operational pipelines of these industries, we have encountered that they do have a lot of optimization problems. And optimizing flights, optimizing routing problems, all of this is something that we can take in a very straightforward manner. The other problems that I think those make us very, very much unique are the quantum problems. So problems in the quantum chemistry sector. I'm a quantum chemist by training, and I used to work in drug design. I used to work in identifying different molecules that could avoid certain reactions to happen in the body that were associated to diseases such as cancer, Parkinson, or Alzheimer. And all these simulations that I was doing were computational simulations, and I was doing them simulating the quantum system. So we can actually have these quantum simulations at small scale at the moment, not at a big scale, but we can simulate quantum chemistry problems with our quantum devices. So this is something that our analog system could do. And one of the nice things that I think we have is that we offer this tailored guidance to the problem. So we offer this development of this app-specific chip that depends on the use cases. So if any company, any stakeholder wants to explore how we can work together to bring a solution that is adapted to that specific problem and that specific client, this is something we can talk about, and that is something that we do differently, because we really strongly believe that in the state of the technology that we have now, the way forward to bring some quantum advantage as soon as possible is to try to maximize the quantum capabilities by bringing together all these two aspects of the quantum technologies, the algorithms and the chip.
Mm-hmm. Perfect. And for anyone interested, I'm going to put links in the description as well for your webpage and contact details so that they can get in touch. But Marta, with that, thank you very much for taking the time. I really enjoyed the discussion, and I hope you have a great rest of your day.
Thank you so much, Niklas, for inviting us to this amazing podcast. I really enjoyed it.